Thank you. We're going to build some event source systems in Clojure using Kafka in Jackdaw. Just a quick show of hands. Who here has used Kafka before? Keep your hands up if you've used Kafka streams before. OK, good. And how many have you used Jackdaw before? OK, so there'll be something new for everybody here. My name is Bryce Covert. I'm VP of Engineering at a small consulting company called Pelitech. And they say you're supposed to say, something about you. I don't like mayonnaise. This is going to be important later in this talk, so keep that in mind. Like any good Clojure talk, we have to do definitions. So what is an event source system? We're going to start with event. Event is something that has occurred in a certain place during a particular moment of time. And sourced is used as a verb here, past tense, meaning that the event source means to give or trace the source for something. And the source in this case, the noun, is the event. And the something is the state. So you can think of it as the state is sourced by the events. So to give an example, the state, OK, that looks right. It doesn't look right on my computer. The state is Bryce is not hungry. An event might be Bryce ate a sandwich at noon. Neither of those encompass an event source system. An event source system would say, Bryce is not hungry because he ate a sandwich at noon. So is it sufficient to say that an event source system is a system that permanently retains traces for everything that occurs? Like, is an event source system just an append-only ledger? I don't think so. I think it's better to say, that event source system is a system whose state is entirely composed of the events that we can trace back to. Another way of saying it is the state of the world is a function of the events that have occurred. So why would you want to build an event source system? If you go in your browser and you go to datomic.com, you'll see this phrase. It's a transactional database with a flexible data model, elastic scaling, and rich queries. All those things will be true of the event source system that we build today. Transactional, in this sense, means that an event is a single thing that happened in the real world that we're storing for all time. And that thing either happened or it doesn't, and all of the side effects happen atomically as well as a result of that thing happening. The flexible data model, when we're doing the event source system we're going to be building today, uses Eden. So we can build any kind of event structure that we want. Elastic scaling kind of comes out of the box with Kafka. And rich queries, we're going to be building them as part of our example. Another reason why you might want to build an event source system is you want to limit point-to-point communication. So oftentimes when we adopt a microservice architecture, if you imagine like an e-commerce situation where you're checking out and you're adding a card to your account while you're checking out and you're paying with that card, maybe your checkout service is going to need to communicate with your card service, adding that account to your profile, and also communicating to a payment service charging that card. And that interaction, oftentimes when you do it over HTTP, is not collaborative, right? You could transactionally fail on one and not the other. And the other thing about that is that you have to know in advance everything you're going to do with that data. You can't say, oh, actually, when someone adds a card, I want to go and capture these kinds of metrics. Oh, interesting. There we go. Pardon the interruption. You have to know in advance everything that you want to do with that data. You can't do, say, analytics after the fact with that data. Additionally, if you build an event source system right, and you're saying the state of the world is a function of all the events that have come before it, you can do simulation. You can say, well, what would happen if I changed my behavior in this way? Or also, like, what would happen if I got events of this format? What would my state look like? To give an example of that, we just talked about how Bryce might not be hungry because 5 minutes prior, I ate a sandwich. But what we didn't cover is, what if that sandwich has mayonnaise in it? What am I going to be 5 minutes later? I'm still going to be hungry. In fact, I'm going to be angry because somebody put mayonnaise in my sandwich. So What you're able to do is you're able to play out those scenarios, see what the state of the world would be as a result of different events happening, and then you're also able to say, well, maybe the behavior was wrong all along, and we want to implement something else to make decisions based off these events. And so you can go back in time and you can say, if I had fixed this bug earlier on, what would the state of the world look like? And we'll look at examples of doing that. Additionally, an event source system allows you to reconcile against the raw events. Oftentimes, you have something that happens in the real world. It triggers something in different systems, and so you want to reconcile between those systems. So system A says, well, my state is Y, and system B says, my state is X. Which one's right? Even if I determine that your state is right and I overwrite my state with your state, what if there's events that are still on their way to me and I'm going to reprocess those and actually come to a wrong result, and actually synchronizing with you makes it worse. If you're using an event source system, the thing you're actually reconciling against is all the events that have happened before. So you're not comparing against the state, you're comparing against the thing that drives the state. Finally, an event source system can be recoverable. If my thing dies and it's down for an hour or a day or something, and it comes back up, do I arrive at the exact same conclusion that it would have if the system was up the entire time? Event source systems lets us do that. So there are a couple approaches that kind of build event source systems that we're not going to do here. So most commonly, a lot of people use webhooks. If you give me a URL, I'll do an HTTP post anytime something changes to you, and you can do that, and you can take that and materialize some state as a result of those things happening. But what happens if your system's down? Do I have to keep doing retries with exponential backoff or something to you until your system comes back up, and then overwhelm you with a lot of traffic once your system does come back up? Or maybe you say, I'm going to put a queue in front of my service so that when I take my service down, I come back up, I can pick up exactly where I left off. But oftentimes, queues only allow single consumers. And once you've consumed from the queue, you can't actually go back in time and do any of that simulation or replay that we talked about. You could also use a pull-based model. You say, I don't care about real-time data. I'm just going to come back to some system of record, ask for everything that's happened, compute by state, and do that on some interval basis. But then, of course, you have more latent view of the data. And you have to make sure that what you do is idempotent. If you go back and fetch the events, you have to make sure you don't reprocess something that you already did earlier. So what we're going to do is we're going to build an event source system with Kafka, Kafka Streams, and Jackdaw. There are other viable approaches to do this. You can use Flink, Spark streaming, and Akka streaming. I've never used any of them before, so your mileage may vary with them. The overall picture that I get from them is that they're a little bit more polyamorous with the different ecosystems. Kafka Streams is very tightly intertwined with the Kafka ecosystem, and it preserves a lot of the guarantees that Kafka gives you, namely ordering in exactly once delivery, which I'm not sure if these other systems do. But you can check those out as well. A lot of what we'll look at here, I think, maps to the APIs that you see in these streaming approaches. So we're not going to talk about mayonnaise and sandwiches for our events. I think that would be a little bit boring. The example that I want to go through is looking at a stream of events from airports where we would get an event stream that says something like, this flight, a passenger boarded. And then this flight, the plane departed, and then it arrived, and then the passengers depart. And we're going to solve a few use cases with it, but just so we're on the same page about what those events look like. In Kafka, everything is always a key and a value, so every event in our system is going to be composed by these two key values and these tuples here. So each of these events all share the same key, that they're all for flight UA 1496. This is saying Leslie Nielsen has boarded 1496 at this time. The next event says that flight 1496 departed, and this is when it was scheduled to be departed. The next one says that it arrived at its destination, and finally that the passenger departed. So everything that we look at are going to be using events of this structure when we're solving a few use cases. So what we're going to do is we're going to do some analytics, some query, and some decisions. And how I'm distinguishing between analytics and query is that query essentially, analytics is what you can know at the time at which the event happened. So I'm going to go and do some processing on the events that are happening. I can say, if a flight leaves and a flight departs, a flight departs and a flight arrives, I can find out how long that flight was. So we can also say which flight's left on time and who's on the plane. But query is about saying, I don't know everything that I'm going to ask of this data after the fact. So what I want to be able to do is form some kind of store where I could say, these events are happening. Are my friends on the plane right now? And ask questions of the stream of events that have happened. And finally, decisions, which is basically side effects. I take the stream of events, I make some decision to do something, and then we're going to look at also what it would look like to fix a bug in that decision-making process and cover some of those replay scenarios we had talked about. So I'm going to do a quick, really high-level overview of the three components, Kafka, Kafka Streams, and Jackdaw. I know most people said that they have already used Kafka before. I'll do a really, really quick overview here. Part of my terrible handwriting. But essentially, Kafka is a multi-producer and multi-consumer model, and how it differs most from a queue is that all data is stored in an append-only fashion. So when somebody's consumed from Kafka, the data isn't erased. You are only moving your pointer forward. So essentially what happens is if every record is a key and a value, the key is used to determine which partition across a series of brokers to write your record to. So essentially, if we see topic 1 here, broker 1, which would be a single server, has 3 partitions of topic 1. Broker 2 has 2 partitions of topic 1, and broker 3 has 1 partition of topic 1. When you spin up a Kafka cluster, it does all of this kind of balancing of the partitions for you. But what happens is that this key is hashed and modded to figure out which of the partitions to write to. So you get a lot of throughput through from this because every producer is producing to every broker. And that's why all these arrows go everywhere. Similarly, when you're consuming, you create a consumer group. And that consumer group can elastically scale up and down, and Kafka will automatically rebalance. And the consumer group has a series of offsets in each one of those partitions, and the partitions are assigned to individual consumers in the consumer group. And as they process, they commit their offset, moving them forward one event at a time in those partitions. This is kind of key to what we're going to be looking at. So if anybody has any questions about that, I'd love to answer that now.
Sure. I didn't quite get what you were saying about it advancing within the different partitions.
So what ends up happening is your consumer group here is going to, actually it might be a little bit easier to see here. Oh, probably should have done it over here. Oh yeah, there we go. So here is some sample code that creates a producer and a consumer. And essentially what happens is you subscribe to be a consumer of an individual topic. And as you poll, by default, what happens is this code looks very similar to what you might have in a persistent queue. But what happens is as you poll, instead of acking the messages from the queue, what ends up happening is you commit your offset. So it would be something like if your offset number was 100 and you get 10 records, by default, when you poll, it's going to commit that now you're at offset 110. And so it doesn't do anything to the persistent storage in Kafka. All that data is still stored. It just knows that you are at an individual index in these lists. Does that make sense?
Which side of the communication is storing the offset?
The brokers. That's actually a really key thing about it. It's a great question. So what ends up happening, let me go back to the previous slide. So what ends up happening is all of the state management about where you are is stored inside of Kafka automatically. So when you pull some records, you can also commit manually when you say, I've done all the work that I need to do. What's going to happen is you tell the broker that information, and it's going to store where you're at. So if that individual process dies and comes back up later, it'll pick up exactly where it left off with no state inside of the consumer consumers themselves. Similarly, if that process dies and never comes back, it'll rebalance the partitions, and it'll assign that partition that you were listening to a different consumer in the group, and then those consumers will pick up where that process that died left off. Does that make sense?
So each broker is going to track any consumer that it's interacting with?
Yes. Yes, that's right. And as a whole, in a consumer group.
Okay. Are we looking at some kind of random sharding thing here, or do the three brokers have very distinct roles?
It's a good question. That one might be a little bit outside of the scope of this talk, but essentially the key, it's not random sharding, it's based off of the key. And so what you do is you get to decide which partition your events go to, and then the idea is that if ordering is important, Kafka guarantees ordering within the individual partition, but not across partitions. So the way to think about it is, if ordering matters, you want the key to be the same for everything that ordering matters for. Does that make sense?
Yeah, and I imagine at some point they flush they don't keep every...
That's configuration. That's configuration. We'll talk about that a little bit in some of the best practices at the end.
I think I get it.
You said when a new consumer comes back up, the broker basically assumes it's a new consumer. Do consumers have identities so that if you bring one back up, it can basically say, hey, I am consumer X?
That's a good question. I think so, but I actually can't recall. But the group has an identity. And so it understands the balance behind the group. I don't know if that process comes back up if it just assumes you must be the same one or not. I don't know. We can look it up at the end. Yeah. So really quickly, we're going to come back to this slide. It's essentially what I'm trying to highlight here is that the producer and consumer code looks a lot like what you would get when you're producing and consuming from a queue. And this is why I think Kafka, a lot of people think about it as a queue, but as we'll see in this talk, it's actually a lot more. So this is, you create a producer for an individual topic, you produce that topic with a key and a value. You subscribe to a topic, it keeps track of your subscription, you pull some records from it, you do some processing, and then you loop for all time. But if you imagine trying to solve some of those use cases we talked about, it would be really difficult to do with just the producer and consumer primitives, and certainly if you wanted to have transactionality as you process it. So Kafka Streams is where this gets really interesting, and that's where most of the hands went down. Let's talk a little bit about some of the prior art. Kafka Streams, if you think of the producers and consumers as kind of like seeks in Clojure, Kafka Streams is kind of like the transducers of Kafka. So it's the idea of separating the plan from the execution. You build up what you want to do, the kinds of processing you want to do, and instead of just iterating over records, you're able to filter and map and reduce them. It's very similar to, has anybody here used Netflix's RX? Wow, that's the least hands I've seen for that one before. But anyways, it's similar to that. It's also similar to Apache Samza, which was actually the predecessor to Kafka Streams. It's a lot of the same people who authored Kafka Streams. So what Kafka Streams allows you to do is say something like, we have our flight events topic, we want to turn that into a stream, we want to split it out from our departures and our arrivals, and that's based off of those keys, the flight number, and then we want to join the departure to the arrival with some kind of window, how long they have to see each other, and then calc some duration, how long between those two events, and stream that to a flight times topic. So it allows you to use a lot more functional paradigm as opposed to just imperatively iterating over all the records in the stream. So here's an example of using Jackdaw to do filtering out just the departed events and emitting them into another topic. So we say take our flight events topic, filter it where the event type is departed, and go and write it to a flight departed events topic. And you're doing that basically declaratively, separating the plan from the actual execution of that. When you do this, Kafka Streams creates what's called a topology, which is that plan, and you start up a bunch of workers in your consumer group with that plan. So really quickly, we'll go back to this plan of what we're going to build, And now, knowing some of this nomenclature, we can sort of break these categories out a little bit further. Analytics, we're going to call taking a Kafka topic, doing some processing on it, and putting it in another Kafka topic, like what we just saw. I just want the departed events in this other topic. Querying is taking a Kafka topic, doing some processing on it, and sticking it in some kind of store where we can ask questions of it later. And then decisions is taking a Kafka topic, doing some processing, and doing a side effect from that. Any questions about that? Great. So let's jump into my demo. I kind of have a Jimmy rigged share here, so give me a second to reset this. OK. How's the font size? Is that good for everybody to read? How's that? Good. OK. OK. So I'm just going to go over a couple of functions that we're going to use here. Essentially, we have a function for producing to a Kafka topic. This is essentially the same code as what we had just seen there. And we're going to take a look at how to start one of these Kafka streaming applications. So this is in contrast to that do seek over all the records. This is how you take a topology, an abstract plan, and execute it. You create with Jackdaw. You create a streams builder. You create a topology from that streams builder. I have this thing that's going to print out the topologies for us so that we can look at what it's doing behind the scenes. And then effectively, we start the process. So one of the things that's really nice about this, as opposed to some other streaming paradigms, is that these are just plain Java processes. You can have a main on it, start a Kafka stream processor, and essentially all of the semantics about sharding and who does what work is all taken care of by Kafka. So essentially, all we have to do is start a worker in our consumer group, and it sort of takes care of the rest. So I also have this function that we're going to be seeing used here a lot that basically all it does is subscribes to a series of topics and prints them out to the REPL here so that we can understand what's happening as we do some of our use cases. So what I want to do is start with something kind of easy. We are going to find delayed events from our flight events topic and write it to a new topic called flight status. So let's take a quick look at how this would work. So this looks not too dissimilar from the example that we started with, where what we do is we take our flight events topic, we filter them down just to the departed events, because what we're trying to do is we're trying to identify which flights departed late. So we filter down to the departed events. The events themselves have a scheduled departure field on them. So if the scheduled departure is maybe a better way to say it is that if the time that the flight left is after the scheduled departure, then we want to emit an event saying that the flight left late. And if it left on time, we want to emit another event that said it left on time. We want to take that data and stream it to a flight status topic. So any questions about that? Because that's going to be the simplest example we look at here.
I don't quite understand the relationship between multiple consumers in this case. So you're creating a stream, right?
Yes.
Does that commit, reading from the stream, does that commit on the Kafka topic on the broker side? In other words, would another client be able to read that data again and maybe filter the same stream for different?
Yeah, the answer there is that it depends. There's essentially what happens is that within a consumer group, only one consumer is assigned a partition in a topic. So if you had 5 partitions and 2 consumers in a consumer group, Kafka is going to give 1 2 and another one 3. That being said, there might be a situation where you care about all of the data from all all of the partitions. And Kafka streams, we're not going to get into it here, but there's what's this idea of a global Ktable, where you say, I want to subscribe to all the information. But you can also spin up separate consumer groups that all have their own offsets. So separate apps that are listening to the same streams. Does that make sense?
Yes, but essentially for a single consumer group, the data are read once.
Let's say 99% of the time, yes. Unless you explicitly want to do otherwise. Yep. Okay. So I just started this topology. I'm going to show, I'm not going to go into them for all of them, but this roughly describes the plan that the Kafka Streams library builds for you. This is like what you would have to do yourself if you were just going to do seek over all of the records. So we take out the flight events as a source. It puts it into this filter processor. It builds this filter processor and then dumps it into this second processor, which maps over them, and it's a bunch of stuff that ultimately ends you in this flight status topic. So when I started this, I said I did a few things. I shut down whatever was running before. I started the topology that we just looked at the code for, and I'm monitoring both the flight events topic and the flight status topic. So I'm going to produce a single event to the flight events topic that departed late. And what we'll see is we'll see in our flight events, this is my produce, just essentially the same information that we just produced. And what comes out the other end out of our flight status topic is the same key, the same flight, but that it left late. And similarly, if I come and, if I emit one that left on time, i.e. that the scheduled departure time and the time that the flight left are the exact same, I get an event coming out saying that it left on time. So the idea there is that gives you some level of abstraction. If you had multiple consumers that wanted to know which flights left on time and which ones didn't, you could put all that logic in one place and allow downstream systems to consume it. Let's take a look at a slightly more complicated example, asking the question, how long is the flight in the air? So same thing, we're going to look at a topology, and I'm going to listen to flight events, that's what we're producing to, and flight times. So actually, I'm going to start with actually doing a demo of using it first. So here I'm going to emit an event for the flight departing at midnight on 3/16, and also the flight arriving 3 hours later. And you can see that we get 3 events coming out. So the first 2 are the ones that I just produced there, the flight departing and the flight arriving. And then we had this processor go and calculate the time, the total duration of the flight based off of those 2 times. I'm going to show another example here. And I'm going to wait 10 seconds to show one of the flaws in this approach, where the way that these 2 events, if you remember that slide that showed the picture of the stream being partitioned into 2 separate things and then joined together, you saw that I had that little join window at the bottom. I said you have 24 hours for the events to come in. In this case, I used 10 seconds. So now I think 10 seconds has passed. So I do my arrival event, and you can see that I didn't get here. There's no event that came out saying that the duration for that. And that's because I set it up to be 10 seconds. Let's take a look at how this topology works. So it starts very similar. I start with taking my flight events topic. I split it into 2 separate streams, one for all of the departures and another for all of their arrivals. And then I take those, well, the font's a little bit difficult here, sorry. I take those departures and I join them with the arrivals. And you can see that you have to set a join window here. And the basic idea is that if you don't set a time window, and how join works is it says if 2 records have the same key, join them together just like how you could do with a foreign key in a database. Well, if you allow that for all time, you're joining everything in that stream with everything in the other stream, and that would be very, very slow. So the typical pattern here is to use a window. So here I said 10 seconds. If there's in the real world, of course, these events would be separated by hours, so 10 seconds is not enough to actually match those two together. But what I do, when you join, you provide a function that says, how do I combine the two things that were joined, right? And all I'm saying here is take the time of the departure, take the time of their arrival, and get the duration of the seconds and emit that to our destination stream, which is flight times. Any questions about that? Well, you might be looking at that and go, well, it seems like you can only do stuff if things happen in real time close to one another. And Kafka Streams has some functionality built into it. Actually, we'll jump first to this K-stream approach. So I put this little example here. And this is a little bit of a clue to your question that you asked a few minutes ago. So a K-stream, everything that we've been doing so far has been with K-streams, where we say, take something out of a topic and do this, do this over the series of things that happen. K-streams allow you to effectively, have you ever had a sequence of stuff and you want to group it, but do a reduce on the values? So like, I want to group a bunch of events by the person, and I just want to know the most recent thing. So last as a function applying the values. That's kind of what K-streams allow you to do. If you have key 1 and an event key 1A, and key 1 and key 1B and key 1 and key 1C, how do I combine those into one view? So I'm not comparing all time for all events. I want to do a group by the key and apply some function across all of the values over time on that key to produce one value. So in our case, we want to know what the most recent departure is for a flight. So if the same flight is scheduled day after day after day after day, I don't want to join to the flights that left yesterday. I only want to join against the most recent flight. And this is called a Ktable. So if we look at the implementation for this, it's really not that different. We take the arrivals is the exact same as we had before, where we just take the flight events and we filter them down to the arrivals. But how it works for the departures, we do the same thing where we just filter down to the departures, but we group by the key. And remember, the key here is the flight number. And then we apply a reduce. And reduce here actually is not, this is kind of an annoying thing in Kafka Streams. Reduce does not mean the same thing that reduce means in Clojure. There's like an aggregate function that we'll actually use later that means what we mean when we say reduce. The main difference is that you can't provide a different type for reduce in Kafka Streams. So here what we're saying is that we have this big stream of events. We've grouped them by the key. How do we combine all those values into one value? We always take the last one, right? So how do we combine V1 and V2? We throw V1 away and we use V2.
So you can only reduce to that particular, the type of the object you're reducing over? You can't like produce a...
You can't start with something different. So like if most common time people see reduce, they'll see like a reduce with a plus, right? And so what you'll do is you'll have like an initial value, right? And that initial value could be an empty list, it could be a number. Here the idea is your initial value is always the first value. You can't set up an initial value, and aggregate lets you do that. Does that make sense?
So just to bring it back to what you were saying before about in the very beginning where Kafka is a function of events that give you a state.
Yeah.
Or what we're trying to do is we're trying to track the state of the flights. Is that right? Like, what is the most recent state of this flight?
Yeah, it's in this case it's like the most recent departure for this flight. Yep. So, and we'll look at why that's relevant here. So this is almost the same code. We replace that join with a window. You don't really see this in when you're using Jackdaw. All of these wrappers that we see here in Jackdaw of filter and left join and stuff like that are wrappers on the same exact functions in Kafka Streams. But when we do our left join here, we don't have to provide a window because the departures is a Ktable. It's not a stream anymore. It's not a stream of everything that's ever happened. It's only, in our case here, one entry for every flight, and that entry is the most recent departure. So we have the same exact function to combine them, but now we don't have a time join window. So if I go back to my example here, it's not this one, this one. So this is the topology that we just built, and if we emit a departed event, followed, I'm not going to wait the 10 seconds here. You'll just have to trust me because we didn't actually have a time window in our example. That it would work for all time, and that state is preserved. Any questions about that?
I have a question. So you said that the records are kept on the Kafka stream for a while, right? So what happens if you lapse, or I guess is there a case where that, like the previous flight, or departure flight goes off the stream and then get there?
In that case, so you've fast forwarded a little bit in the conversation. So one of the cool things about Kafka Streams is it actually gives you a database on the processor itself, and if that record fell off, it's still in that database, meaning that key is still present in that database. But if you say destroyed that instance and replaced it with another consumer, then that data would be gone forever. What I recommend to resolve that problem is instead of using a retention policy in Kafka, you do compaction, which is to say, I want to make sure I always have at least one event for every key. Don't throw away the last event, even if it's outside of my window of how long I'm keeping data. But that's still a plan B from keeping all data for all time. Yep, great question. So the next thing we're going to cover is how to tell who is on the plane. So just to give a little example here, I'm going to run it first. So I just started the stream, and I'm listening to same thing here. I'm monitoring two topics here. I'm monitoring the events, that's what we're emitting, and a topic called passenger, which is going to say for anytime the people who are on the flight changes, we're going to get a passenger event. So I'm going to put Leslie Nielsen onto the plane, passenger boarded, and you can see that like all the other examples, we emitted our event for passenger boarded, but we also see an event in our passenger topic saying that we've added Leslie Nielsen to a set of passengers. We're going to look a little bit later at how what I'm about to show here works, but we can also query the running app and say, who is on the flight right now, right? So what we see down below in the REPL is just emitting what's happening in a stream, but we can actually ask live questions to that state and say, who's on the flight right now? And we can see that Leslie Nielsen is on there. Going back to the questions about how you partition things, it's really important that the key is the flight number here. Otherwise, you would only have some part of the data because otherwise it would be randomly distributed through all the partitions. So you really want to make sure that the data that goes together shares the same key.
Brian, how would I go, say, a week from now and say, was Leslie Nielsen on that flight? Is that a different topic? It's different, sorry, not a different subject?
It's like you need to know all of this stuff and some more stuff. So let's talk afterwards. There are solutions for that. If you just want to like Google it later, you would need a custom queryable store. Yep. Now we're going to have Leslie Nielsen depart the flight, and we're going to see that we emit a new event on our passenger topic that says that now there's no passengers on the plane. So let's take a look really quickly at how that works. So what we do is we take this. Every one of these is going to follow that exact same model of taking our flight events, and we're going to take the stream, and we're going to create a passenger. it's misnamed here, sorry. We're going to create a passenger Ktable. So what we're going to do is we're going to filter it down to just the passenger boarded and passenger departed events. And we're going to do that same thing that we just saw before when we were trying to find the departures. We're going to group them by the key, and instead of reducing, this time we're going to do aggregate, which is what like we in Clojure world call reduce, where we can set an initial value. And what we say is we want to start with an empty set, and then for every passenger, for every event that's a passenger boarded or a passenger departed, if they boarded, we conj onto the set, oops, and if they departed, we disjoin from that set. And any questions about that? So what that does is it gives us a Ktable just like what we saw before, but now what we want to do is we want to take that Ktable, which is just a current snapshot, and we want to stream the results to a topic. So essentially, you can take K-streams and aggregate them into Ktables with some aggregation, and then stream those aggregated results to topics for further use. And that's what we're doing here. We're saying emit an event that just has a snapshot of what the current passengers are to a topic, as opposed to what we did before, which we just said we have a table of departures. We didn't use it. We didn't stream the departures anywhere. Here we're streaming the passengers to another topic. What we'll do? Oops. We'll also take a look at, sorry, I meant to actually put 2 people in here for later in the demo. So here I have Leslie Nielsen and Julie Haggerty on the plane. And now we want to move on to another use case where we're saying, as people are boarding the plane, we want to include how many people are currently on the plane. So it's something like, as people are boarding the plane, we'd like to have some system that says, hey, maybe we want to have like number 100 get a prize or something like that. So as we want to take the events, do some processing, and then decorate the events with the number of people that are currently on the plane. So let's take a quick look at how that's going to work first. So I'm going to have Robert Hayes get on the plane. And it's gonna take a second here, but we should see an event that says maybe. So I think right now it's actually creating a topic, and sometimes there's some latency there. Let's try this again. This is the problem with doing live demos. Let's make sure I started this right. I'm optimistically still thinking it's starting up. So, oh, yeah, I'm right. Okay, so now what we do is, so you can see that the 2 topics I'm listening to up here are that we're monitoring the flight events, that's what we're emitting, and the events with the passengers. And so the idea is that as things are happening in the system, we're augmenting every event that comes through the system with how many passengers are currently on it. So it's the same event, but now downstream consumers can know there's 3 people on the airplane. And as somebody, say, departs, this will actually go much, I have to go find a departed here. As if I have Julie Haggerty get off, now it goes down to 2 that you can see here. So let's take a look at how that works. So this is very similar to what we did before. We take our flight events, we create this lookup of the flight to the set of how many people are on the flight, and we take out of the Ktable. This is actually kind of a nice little feature of Jackdaw here, is that it allows you to, in Kafka streams, there's a Ktable object. And this sort of Ktable star function here allows us to get at the raw Java object so that we can ask questions of that Ktable. And here what we're saying is, we know that you're storing this state as things happen. I want to get a queryable view of that state. And and that's what this passenger store name is. So then we take our flights, and what we do is we do this, it's kind of dirty here, this transform values. And this exposes a little bit of like what you would be doing if you weren't using Jackdaw. Transform values is kind of like the jack of all trades function. You can take one value and turn it into 10. You can take one value and filter it out and emit nothing. It's something like what Mapcat does, or folding. So the idea here is that we actually have to like reify a Java interface here. But what we do is the reason why we're using transform values here is that when you transform values, you can actually ask the stream, Kafka Streams library for queryable stores. So we've looked at these examples of keeping track of everybody who's on the flight. This is saying as we transform the values, we want to ask that store about who's on the flight. And so essentially what we do here is we have an atom that stores, that has this state store in it, which is, you can think of that as like just a hash map. And what we're doing is we say every value that comes in, ask the state store for the people that are on this flight, then count them and associate a passenger count onto the event. So we're able to build these like materialized views of all the events that have happened and then use them as we're transforming our events. Unfortunately, it's got this really gnarly, terrible syntax here, but we'll take a look in a second at how we can improve that. Well, actually, we'll take a look right now. This value transformer thing is really just a terrible way of being able to provide a function that includes these queryable state stores. So what I did here is I basically just pulled that logic out to create a thing that does that same transformation in, and you just need to pass in the function that you want to apply on every event that comes to the system and the queryable stores you want to use. So what that ends up looking like is like this. So we can do transform with values. We say we want to use that same passenger store name, but we don't have to do any of that like reification of those Java interfaces. Any questions about that? Yeah.
Mostly, what is Jackdaw buying you over using the raw KStream interfaces? Because they look kind of similar.
Yeah, that's a great question. I think that it mostly is just a wrapper, but it's like a really good one. So what I really like about Jackdaw is I know all the KStream and Ktable implementation pretty well, and I can transform that really easily into the Java, the Clojure equivalents of it. And so it's almost like if you said, I want to use Kafka Streams, but I don't want to create all these interfaces and stuff like that, you would basically create Jackdaw. What's nice about how they've done it, though, is that they've also added, it's basically like these wrappers plus the stuff that you would need if you were doing it in Clojure. For example, in Kafka, you use these serdes to serialize and deserialize. Well, there's no out-of-the-box Eden serializer. It gives you that. So it's kind of like if you were going to create the tool chest to use Kafka Streams in Clojure, you'd probably come up with something very similar to Jackdaw, but not covering everything. It's a very thin wrapper, but it makes everything look almost completely idiomatic Clojure, which I really like. We're going to move on to looking at, now that we've looked at these examples of building these queryable stores and using them, I want to look at being able to answer questions at runtime. Like if you remember, we were talking about how do I ask these stores, are my friends on the plane? And we've used this a few times, this function, this query get passengers, to say, what's the current state of the world? If you were building an HTTP service, you could do this, right? You could do your Kafka Streams processing, build these state stores, and then ask that state store a question, as opposed to going and dumping it in a database to query. You can use the Kafka Stream as the database, and it's actually very fast because the database lives. It's under the hood, it's a RocksDB database that lives on the same process. So what we do here is that when you start a stream, it gives you this Kafka streams object. In all these examples, I've just stored it in an atom here, and every time I start a new sample, I shut it down and start a new one up. But you're able to ask that stream for all of those queryable stores. So when we look here at all of these topologies, you see that we actually have these stores that we use along the way, and we can ask that topology effectively for give me at runtime when you're running something that I can query. And using that, you can use it just like how we use it in our stream processing. We can use it as a way of at runtime asking questions of the stream processor. Tell me how many people, or actually who exactly is on that flight. So if you could imagine like building some kind of HTTP service, your HTTP, the thing that's actually serving the request, can use these state stores, while the thing that's driving the state stores is actually running in that same process. We also can ask questions like, my friends are Leslie Nielsen, Julie Haggerty, and Peter Graves. Are they on board? And this tells me which of my friends are currently on board. And we can see that that's true. It's just a set intersection between the people who are on the plane and the people that I'm asking about. Any questions about that?
I'm still trying to unwrap what the difference is between analytics and query. Because if I think about each of them, I think of each of them colloquially, I suppose. Like.
So I think that analytics is the way I distinguish between them here are the questions that I know while I'm doing the streaming. You don't know who I'm going to, in this example here, when I'm asking my friends that are on board, I don't know who the friends are. You might have different friends than I have. Or it might be a user is actually querying the system via HTTP or some process to say, give me some information, and you don't know all of the parameters across which they'll be querying in advance, sure. Right?
What's analytics in contrast then?
Analytics is doing calculations for downstream systems to further use. So meaning the example that I gave of the 100th passenger, right? You're not going to use something at runtime to query the state store to find the 100th passenger. You would subscribe to the stream that says, listen for everybody that's boarding, wait until I find the one that's the 100th passenger, and then give them their free drink prize or something like that.
And would it be like analytics are sort of part of the topology effectively? Like
Yes, that's exactly right. So in that slide I showed that analytics you can think is Kafka stream to Kafka stream, and query here is Kafka stream to something that I can ask questions about later. So the last example that we're going to look at here is making decisions based off of the streams. So this looks very similar to what we've seen so far. But when we say make decisions, typically the way that I think about this is that a decision, the events are all observations. So a decision is saying, given those observations, I want to do something, right? In this case, I'm just what we're going to do is we're going to say when the last passenger leaves, I want to tell somebody to clean the plane. The way that I think about that is we have some business logic that we apply to the streams. We may decide to do this side effect. Before we do that, we write our decision to another topic. Typically, you don't want to intertwine those two because the flight events, in this case, are things that have happened. You don't have any say over whether that happened or not. But the decision to clean the plane is something that our business logic derived from those events. And so you don't want to intermix them there. So what we're going to do is we're going to listen to the flight events, we're going to wait for the last person to leave, and then we're going to emit a decision to clean the plane, and then do a side effect as a result of that decision. So I'm going to start this stream processor up, and I'm going to say Leslie Nielsen got off the plane, Robert Hayes got off the plane, and Julie Haggerty got off the plane. And you can see here that it made the decision at that moment to clean the plane, and it also, my side effect here is just print lining I told somebody to clean the plane. Maybe it sends a text message, something like that. So let's take a look really quickly at how that works. So we use a lot of the same primitives. We take our flight event stream. We have a Ktable of the flight and everybody who's on it. We grab our queryable store that we can ask for who's on the flight. And what we do is as passengers board or leave the plane, we associate how many people are on it based off of that store. And then we filter those down to the ones where the event was that a passenger departed, and as a result of that passenger departing, there's 0 people left on the plane. And then what we do is we map that into a decision. So we basically say the decision is to clean the plane, and we take everything off of it. Really, the only piece of data that we actually want to keep is the time, and that should have been that should actually still be included in there. But then what we do, so every other example that we've seen so far is we use the to function, which says, like, put the output into this stream or into this topic, and I'm done. Through says, put it into this topic, and I still want to do some more stuff after putting it into that topic. And that last thing that we want to do is this side effect to clean the plane, right? So here we the idea of process is it's something that you're going to consume everything that's coming through the stream without emitting anything to any other stream. It's the sink. It's where everything ends. So I want to give you guys one more example of behavior that you can do with this. And let's say we found a bug where the last passenger leaves the plane, but then someone left their coat behind. So they get back on the plane, and then they come out one more time. And our system said, oh, now they've got to clean the plane all over again because someone came on and grabbed their coat, right? There was a bug in that behavior, right? My code doesn't handle that. Right now, it would emit that side effect 2 times. I haven't written the code to actually say fix that bug. It's not super relevant here. I just want to show an example of what if we wanted to go back and say, like, go and fix that problem and fix the state of the world, right? Change the decisions that we would have made as a result of that. And so we're running the same topology here, but what I've done is I've given my application a new ID that this is like after that bug fix, and I'm also associating some other configuration that says if this application is just starting up and I don't have any offset, I'm nowhere in the stream, where should I start? Up at the top in this application, everything that we've done has started at latest. Essentially, I didn't want to go process everything that happened before. But what I can do very easily is spin up something new or spin up something like a bug fix here and rerun it from all time. So this will take a second, but you can see here that it literally just ran through every event that we've done in this demo all over again and re-emitted the decisions. And you can see here that it's tried to clean the plane several times because we loaded and unloaded the plane several times. So you're able to you can very easily say, I've got some new behavior and I want to change the behavior from now on. And you can also say, I've got some new behavior and everything that you knew before was wrong, go and start over. And it's very easy to do that. So I want to talk briefly about
the key. What does the bug fix key get you? What does that look like?
The bug fix
You're restarting it from the earliest with this new application config.
Yeah. Are you asking what this value means? Yeah. So that's a good question. I probably should have showed this at the very beginning. So every Kafka consumer has some configuration. Some of it's specific to Kafka streams, and some of it's specific to all Kafka consumers. And for streams, you give your application an identifier. What that does is it uniquely identifies, essentially, if you remember the Kafka picture that I showed one consumer group. If you have a different application ID, you get a separate consumer group. So the idea is that if you wanted to process flight events one way and you have your own ecosystem for processing them, and I want to process those same events in a different way, if we use different app IDs, we don't conflict with one another at all. We have our own set of offsets. And so what we did here is essentially say, this is such a radical bug fix to the system that we don't want to preserve anything that we had before, create it as effectively a brand new application with new offsets and everything. Does that make sense?
New set of streams?
It makes Kafka track a new consumer group. So this.
You're writing the new flight decision.
No. Those are the same topics. Those are the same topics.
You're
Yep.
writing that, but
Yep. But it's a new topology. It's a new point in the world that you're at. And so essentially what these do is it distinguishes different people and where they are in the total stream of events. Yeah.
I don't know how Jackdaw is written, but I do know in Kafka streams that the application ID is tied to the store name. So it's actually like the prefix for the store name. So every application will get their own store to share the streams as a purchase.
That's a good point, because if you had a
I thought the stores were local to the consumer.
They're persisted back to the Kafka broker.
as well. In addition.
Yeah, so what's the difference between I don't understand what the difference between a store and a
K-tables are backed by stores. So you can think of as a K-table as an abstraction on top of the store. Does that make sense?
Not really.
Okay. So you can store data that isn't in a. So think about it this way: the store is a way of interacting with a local RocksDB database, which is a key value store.
Okay. So you just said local, but then.
Yes, and that's it kind of goes back to that point. The K-table is that abstraction on top of that. That's part of the table in the overall topology ecosystem of Kafka streams. I think. I haven't done this, but I think you could create, as an example, custom stores that don't use RocksDB at all, but would still be backed by K-tables. Yeah. Yep. Yep. I haven't done that, so don't quote me on that one. Yep.
And then in the example with through into a process,
yeah.
Is that a T, or does the process consume from the topic that you are putting the events through?
It is a good question, and it goes into, it's a pretty good segue. Let me make sure that I answer that question when I finish this final slide here, and if not, we can follow up afterwards. So you guys are just going to need to deal with my kind of janky setup here as I walk through with the presenter notes here. So we just looked at how you can do stuff with Kafka streams and Jackdaw and Clojure, but I want to talk a little bit about if you were going to build these kinds of systems, what are some things you want to keep in mind? Probably the most important one is determinism, in that you want to make sure that if something has to be ordered together, they end up on the same partition. If you can actually produce to Kafka without a key and just produce values, basically what it's going to do is randomly pick a partition. And what that means is you can't actually have any determinism in your system. Is it going to do the same thing every time that sequence of events happens? No, unless you built that into your behavior natively. So oftentimes you say, well, I actually need a join by these keys, but the keys aren't what I want stuff partitioned by. So let me give an example. If you said, I want to make sure that everything at one airport ends up on the same partition, but I need a join by the flight keys, right? You could still do that in Kafka streams and Kafka natively. You basically pull out yet another key that's your partition key that decides where you want written to, and you can say, I want to write to a partition based off of any value in the key or the value itself. Second thing that's a really good question to ask yourself if you're building event source systems is, imagine you turn one of your consumers off for a week and things back up well, backup is not really a good word to describe it. Things accumulate in your stream that you haven't yet, in your topics that you haven't yet processed. Let's say you're subscribing to 2 topics, one that has very low throughput, one that has a lot of throughput, and then you bring it back up after a week. Do you end up at the exact same conclusion? I would wager that if the answer to that is no, you probably have your partitioning set up wrong. So it's a good thing to keep in mind. One thing that you're going to run into, if you say, my state is a function of the events and only the events, what happens when you make a mistake? What happens, and you can't go back in time and correct it. You say, I emitted this event, some side effect took place in some system downstream from here, and now I need to undo that. Probably the biggest burden that you start adding on the consumers of your streams is the ability to undo something you already did, right? So I emitted this event, I thought it was a departure, but it was actually an arrival. Sometimes the best way to do that is just to re-emit the same event, and let's say the event has an ID, and you just give new data for it. Sometimes you actually have to go much more proactively and say, I know these 100 events were wrong. I got to emit like a void event. These 100 things, whatever you thought they meant, forget about them because I'm going to give you something completely different. It's a pretty high cost in these systems to think about how you handle error scenarios when you have no escape hatches, right? The only thing that drives your state is the events themselves. One of the things that we looked at here was our topic hierarchy. You notice that I always listened to the flight events and emitted to some other event. And even in that decision, you could have said, like, I decided to clean the plane and put that back into the flight events topic. Kafka Streams will let you do that. Take some data from a topic, do some processing, and shove it back into that same topic. But I don't think that's a very good idea. And the reason why is when you make decisions, keeping them separate so that you can actually say, this is like version 1 of this decision. And I might change my logic and optimize it, and being able to replay without fear of breaking the entire picture of the world when you change that behavior. Transactionality. In this example here, I used all of the default Kafka settings, but when you are a Kafka consumer, you can set your delivery semantics to exactly once. So if you think about a queue, you can have at most once and at least once semantics. You could take, at most once would be, I take an event from the queue, I do some processing on it, and, I take an event from the queue, I ack it, which deletes it from the queue, and then I do some processing and do my side effects. If those side effects fail, it's game over. I can't go and redo those side effects because it's removed from the queue. That's at most once delivery. At least once is saying, I take something from the queue, I do my processing, and then I remove it from the queue. But the problem there is, what happens when my processing succeeds, but deleting it from the queue doesn't succeed? I have to make sure that I do that in an idempotent way. Kafka, when you're in the world of Kafka Streams, allows you to have exactly once delivery, end to end. So you can think about it as everything that we looked at here, whether it's writing to the local database or committing an offset of where we are in the source stream or producing to a target stream, all of that happens within a transaction in exactly once delivery. So if you have something, a monolithic topology that's writing to 5 different streams, 5 different topics, the advantage there is you could say all of those happen or none of them. You definitely don't want to have a situation where you, say, are doing bank transactions and one of them succeeds and another doesn't. One of the things that we didn't look at here at all is the event structure. So when you have a very simple domain, like, well actually flights is a pretty complicated domain, but I simplified it a lot here. And you say, well, we're going to use Kafka, which means anybody can use this data. You have to be really careful about what your events mean, because if what we had here was just a few keys and a hash map, but if we have a really complex domain of all of the things that can happen in the system, we have to make sure that every consumer of those thinks about those events the exact same way. And oftentimes they won't, especially if you have, say, 200 different kinds of events. So my recommendation there is to embrace the fact that it's something like the state of the world is a graph, and every event that happens is either adding a node or adding an edge or removing a node, or removing an edge from the graph. And so the way to think about it is think about the state of the world first, and then make your events be using that same state model to say the flight status is now departed. The flight status is now arrived, as opposed to saying flight arrived as the event type. Good luck, figure out what that means to you. Any questions about that? Okay, the last thing that I want to cover here is data retention. So by default, Kafka sets a retention policy. I just said how it's an append-only ledger. By default, it isn't. But you can configure it to store all data for all time. Or you could say sunset the data after, say, 2 weeks. I think that if you cannot stand to have all data for all time, the best alternative is log compaction, where you say, I want to store data for 2 weeks, but if I haven't seen a key, a particular key in those 2 weeks, don't delete it. So you at least have the most recent event for every key, and hopefully you have enough state from that. So if you want to read more about this, if you want to look at these examples, I have it all up on GitHub. And the slides are on SlideShare, which is linked from the GitHub. And there's a bunch of other resources that I recommend you look at. In general, Confluent is a consultancy that consults on Kafka implementation and application building and operations. Their documentation tends to be better than the native Kafka documentation. It's really, really good. It's the basis for a lot of this stuff. But I have a link here also to the Java docs and Jackdaw itself, which wraps a lot of this behavior in a Clojure-friendly way. So that's it. Any other questions? Yeah.
Have you done a lot of these in production?
Yes. I have not done it with Jackdaw.
Okay. How do you make the determination on when you're going to write a stream processor versus write a KSQL transform?
I haven't used KSQL a whole lot. For those who don't know, KSQL is yet another abstraction on top of Kafka streams that allow you to use SQL to query your data in your streams. I haven't used KSQL a whole lot, and certainly not in production. Yeah.
One potential answer for that question is what type of data serialization and deserialization do you need to use? So for example, if you have to use, and I don't remember if this is still the case, but I remember when I was playing around with KSQL, I don't think it handled Avro super well, and Avro is one of the data serializations that's sort of native for Kafka, especially with Confluent. They have their own internal struct type of system, which seems really awesome, but if you're already getting a topic with Avro in it, you might not be able to use KSQL for it.
Anything else? Yeah.
At the beginning, you mentioned Datomic. How does Datomic compare to Kafka?
So I think that the only way in which Kafka itself is similar to Datomic is that Kafka stores data in an append-only system, albeit with some retention by default, and that's about it. Kafka Streams is about saying, if I model all of my processing of those Kafka topics and use this exactly once delivery, then I'm able to work with it in a transactional way, and have point in time time travel essentially in the Kafka topic in a very similar way to what Datomic lets you do. Now, I didn't show any examples of that doing that time travel, but it's fundamentally really well aligned with that. The big difference with Datomic is Datomic can't really support a lot of high throughput writes because it has a single transactor. It's actually pretty good because they keep it really simple, but with Kafka, you're able to basically set up as many partitions as you want, which allows you to parallelize writes. You don't have the same kind of ordering guarantees that you get in Datomic, since everything's serialized in Datomic. It's a great question. Great. Well, thanks, everybody.